Hey friends, it's Miss Adams from Flamingo Math. Let's look on day 2 in lesson 13, unit 4. We're talking about matrices and as functions again. Remember, we can take the composition of two functions f and g, f of g of x, and that same operation is going to hold true for linear transformations of matrices as long as the domains and the codomains match up. Let's look at that general definition of the composition. If we have the composition of T2 with T1 is a linear transformation, then T2 composed with T1 maps U onto W. And we have the same issue in matrix transformations that we do in function transformations. If the range of the transformation from the first vector is not contained in the domain of the second one, then this is not defined. The composition of the transformations are not defined. Let's look at example 6 to get an idea of what's happening in this lesson. If we're given linear transformations, T1, which is going from 2 dimensions to 3 dimensions, and T2, which is going from 3 dimensions back to 2 dimensions, we want to find the transformation of T2 with T1 using 2, -1. And they've given us the definition here, so we want to explore T1 at 2, -1 is going to be 2 plus 3 times -1. I'm looking at this slide here, and then 2 minus -1 for the second row, and then 2 times 2 for the third row using elements x1 and x2, x1 and x2. This is our x1, this is our x2. We're following this rule here. So what does that give us? That's going to give us 2 minus 3, 2 plus 1, and 2 times 2. So we've got the transformation of t sub 1. Then following the second rule, t sub 2 is t sub 1 using 2, -1. That's t sub 2 is going to map onto -1, 3, 4, because we just calculated this part here. And we have 3 times -1, following the rule, plus 4, x sub 3 is 4, and 2 times x sub 2, that's 3, minus 4 times x sub 3, that's 4. So following this rule, and what does that give us? 1, -10. So the transformation, the composition of T2 composed with T1 using the vector 2, -1 maps to 1, -10. And if you go back and look with me exactly at the given directions, you see that we mapped 2 dimensions onto 3 dimensions, and you can see that we get mapped 2 dimensions onto 3 dimensions, and then the T2 mapped 3 dimensions to 2 dimensions. So T2 mapped 3 dimensions to 2 dimensions. Let's move to the next example. Standard matrix for a composition of 2 linear functions. So we want to find the standard matrix for the composition of T2 composed with T1 for the given linear transformation where T1 is mapping 2 dimensions to 2 dimensions using this rule, and T2 is staying 2 dimensions to 2 dimensions using this rule. So we want T2 composed with T1 to map R2 to R2. So T1 times our xy has to be 3, -2, 2, 4. See where I'm pulling those values from. 3, -2, 2, 4 times our vector xy is going to give us a sub 1 times some vector x. Then we want to follow the rule for t sub 2, the transformation for 2 with xy has to give us a 2 and a 0, taking that from this rule here, times some xy, but we need a 2 by 2 matrix to give that, so that matrix would be 0, 2, 0, 0 times xy, and that would produce the second a sub 2 times our x bar. So we want to do a2 times a1. So a2 is 0, 2, 0, 0, and then a1 was 3, -2, 2, 4, and matrix multiplication is going to give us that standard matrix. 0 times 3 and 2 times 2 would be 4, and second row 0 times 3, 0 times 3 and 0 times 2 is 0. First row, second column, 0 times -2 and 2 times 4 is 8. And then second row, second column, 0 times -2 and 4 times 0. This is our standard matrix here. That's what they're asking us to find, the standard matrix. So now that we know the standard matrix, let's suppose that you wanted to find the composition of T sub 2 composed with T sub 1, and we had the vector -2, 3. We could use that standard matrix, using the standard matrix. We would use 4, 8, 0, 0 times -2, 3, 4 times -2, and 8 times 3, and then 0 times -2 and 0 times 3. That composition would be 16, 0. So this is just as a for example. This is just an extra example. If I wanted to use that composition with a different matrix, I could use our standard matrix to perform those operations. Then here in our last example, we want to determine the transformation matrix that describes a reflection in the y-axis, followed by a rotation of pi over 2 about the origin and a dilation by a factor of 3. And you are allowed to use your calculator on here. So putting all of this together, let's think about this. We want to reflect in the y-axis. We want a rotation of pi over 2 around the origin, and we want a dilation by a factor of 3. So one of the things that we need to pay attention to is we want to work from the inside out to make this happen. So work from the inside out. And that tells me I need to do transpose 3, transpose 2, transpose 1 on some x bar. So a dilation by a factor of 3 would be a matrix 3, 0, 0, 3. And then rotate pi over 2. We just saw that in the first lesson. Cosine pi over 2, sine pi over 2, opposite sine pi over 2, and cosine pi over 2. And then reflect in the y-axis means we need to change this first component to -1, so that when we multiply by our x, y vector, we've got the dilation here, We've got the rotate by pi over 2 here, and we've got the reflection about the y-axis here. You see what I mean about working from inside out? So that way we're going in the right order when we work from the inside restrictions out. Okay, so 3, dilation 3, 0, 0, 3, rotation 0, -1, 1, 0, and then our -1, 0, 0, 1 times x, y. So rotating from, or performing those operations inside out, we've got x, y here, and -1, 0, 0, 1. And then doing these two together, these two, gives us 0, -3, 3, 0. So we performed those operations first. And then the transformation for x bar is going to be 0, -3, -3, 0 times some x, y vector. So we did these two last. Make sure I did that right. 0 times -1 and -3 times 0 is 0. 0 times 0 and -3 times 1 is -3. 3 times -1 and 0 times 0. 3 times 0 and 0 times 1. Yes, we did it. Yay! Okay, that's the end of day 2. We have one more section in this lesson before we're done. Join me next time.